So far, we have studied the FIR filters and all the mathematics associated with it. For example, we started with the ideal frequency response and we saw how to calculate the coefficients for a filter analytically, and also we studied the MATLAB function for calculating the coefficients of a filter. We also studied the MATLAB function for plotting the frequency response and finally for doing the filtering. All this we have studied so far. Now in this particular session, what we want to do is to provide some simple explanation for the working of a filter in time domain in order to get better insight into the working of a filter. That is the only objective. Alright. So let us start. So when you filter the signal, basically what are you doing? You are executing this equation where the output is given by the product of the filter coefficients and the signal values. So this is the current value of the signal. You multiply it by B0. This is the value of the signal one sample time earlier. You multiply it by B1 and so on. How many terms? It depends on what is the order of the filter. So let us assume that our order of the filter is 4, or the number of coefficients is n plus 1, that is 4 plus 1, that is 5. So B0, B1, B2, B3, B4. So we'll just demonstrate how the calculation proceeds as you calculate one sample value for the output and then the next sample value and so on. So to illustrate this, we have written this table down. So this xn represents the current value of the input. And I have stored some random values here. So this is the current value. This is the value one sample time earlier. This is the value two sample times earlier and so on. And these values I have written in red because these are the values for which the calculations are done. This is a filter with 5 coefficients. So you require 5 values here, current value, previous and so on. So when you calculate the output for this value of n, what do? Multiply B0 by this value, then multiply B1 with this value, B2, B3 into this, B4 into this, and finally sum all these products. That is how you generate the output. Once this has been calculated, then what you do? You need the next value. So the next value is red, so the current value now becomes this. See, we have completed one calculation and now we are doing the next calculation. So this is the next value. So all the values shift to the left. This is one sample time earlier, this is two sample times earlier and so on. And so now the output value that is calculated will be B0 into 0.2, B1 into minus 0.1 and so on. That is how you proceed. Again, when you read the third value, this becomes the current value and everything shifts to the left. So at any given point of time, you do these 5 products and then take the sum, and that is your output. So in time domain, that is what is happening when the filter is doing its work. Okay. Now what we want to do is, we want to take some simple signals. For example, we want to take a signal which will have low frequency content, one signal which will have high frequency content and medium frequency content, and then see what are the outputs for various filters. Okay. So let us first consider some simple signals. And in these calculations, we are assuming that the number of coefficients is 5. Now the low frequency signal can be, one example of this will be all values same. So the value is not changing at all. So this is the lowest frequency that you can think of, that is essentially a DC component in the signal. So certainly this is a low frequency signal. High frequency signal, where after every sample time the value jumps from high to low or low to high. So we are assuming in most of the filters, it's assumed that the lowest value of the input is -1 and the highest is 1. That is how the scaling is done. So you can see for every sample time, it changes from minimum to maximum or from maximum to minimum. So that is a high frequency signal. Medium frequency signal, it also changes but doesn't change so fast. Here after 2 samples it repeats. Here this repeats after 4 samples. So you got 1 followed by 1, now followed by -1, and then it will repeat again. But we got only 5 values here because the number of coefficients are 5. Okay. So these are some simple examples of low frequency, high frequency and medium frequency. Basically what we want to do is to have some qualitative feel for what is happening when the time domain calculations are done. All right. So having defined the low, high and the medium frequencies, let us now look at some typical coefficients for various filters and then try to see what is the value of the sum of the products for various frequencies. Okay. So low pass coefficient is again 5 values. So first is 0, this 0.28 and so on. Understand, this is one example. You could have other values depending on the window that you are using. But anyway, this is one possible array for coefficients for the low pass filter. So now if the input signal has a low frequency, then let's consider it is this. So how do you calculate the output? This multiplies this, so you get 0. This multiplies this, so you get 0.28. This 1 multiplies 0.4399, so you get this. Then again you get 0.28 and finally you get 0. So essentially it is the sum of these 3 values. All of them are positive and you get a comparatively large positive output. When the low frequency signal is applied to a low pass filter, you get a large positive output. But suppose you consider the high frequency signal, then what will happen? 1 into 0 is 0, minus 1 into 0.28. So this will give you minus 0.28. This gives you plus 0.4399. And this again gives you minus 0.28. So you find that because the high frequency signal has a number of negative values, some of the products are negative, some are positive, and therefore they tend to cancel and you will get low values. We'll actually do these calculations through a program and finally show you the result. But right now, intuitively, we can easily understand that if the input signal is of low frequency, the low pass filter will generate high output, and if it is a high frequency, it will generate low output. Now consider high pass coefficients. So this is 0, now it's minus 0.28. Note that for low pass we had plus 0.28, is minus 0.28. Center value remains same and the next value is again minus 0.28. So now what will happen when the high pass coefficients multiply the low frequency signal? What will happen? 1 into 0 is 0. 1 into this, now this is minus. Okay, so this is becoming minus because the coefficient value is negative, although the signal itself has a positive value. So this will give you positive value, this will give you negative value, and this is 0. So now you find that some of the product terms are negative and one of the product terms is positive here. So you will get a low output for low frequency signal because this is a high pass filter. But similarly, it will be easy to show that if you consider a high frequency signal and do the multiplication. See, 1 into 0 is 0. Now this is minus, this is also minus, so it becomes plus. This is positive. These two minus become plus. So again, all the product terms are positive and you will find that the output of the high pass filter will be comparatively large and positive. Okay. So this shows to you how high pass filter rejects the low frequency and allows the high frequency signal. Similarly, you can talk about the band pass. So for band pass, what will happen? Again, you can do similar calculations and it will be possible for you to show that for low frequency, the output is low. For high frequency, again, it is low. But for medium frequency, when you carry out this multiplication, the output is going to be high. You can test this yourself quickly. But we are going to anyway demonstrate a program which will do all these calculations and give the result in the output. Finally, band reject coefficients. These are the band reject coefficients, and you will be able to show that when you carry out the sum of the products for various frequency signals, here you will get a high value. For medium, you will get a low value, and for high, again you will get a high value. So it will reject the medium frequency signal. That's why it is called as a band reject filter. All right. So whatever we have been discussing the calculation here, what we'll do is we'll write a program in order to do all these calculations, print the results, and quickly see how the high pass filter is working, how the low pass is working, and so on. So that is what we are going to do next. So example program, this is our first statement as usual. N equal to 4, this is the order of the filter. Remember, the number of coefficients is order plus 1 as defined in the MATLAB. So N is equal to 4. So you find the low pass filter coefficients, which I have written as B with a suffix L to show that these are the filter coefficients of a low pass filter. So FIR1 N, that is 4.5. This is the normalized cutoff frequency. And what we are going to do is to keep N same for all the filter coefficients, keep the normalized cutoff frequency same. Now this parameter will decide whether you get the coefficients for low pass filter, high pass, and so on. Again, we'll use the rectangular window for all of them, and we are going to display these coefficients. Okay. So now next you calculate the high pass filter coefficients. It will be similar to this, except that this low will change to high. So all the rest of the parameters are same. This low changes to high. So we call this as BH. So BH array will store the coefficients of the high pass filter. Similarly, you calculate the coefficients for the band pass filter, display. Finally, calculate the coefficients for the band reject filter and display them also. Okay. Now that you have got your coefficients, what we do is we define our low frequency signal, high frequency signal, and the medium frequency signal. So this is my low frequency signal. All the 5 values are 1. This is the medium frequency signal, 1, 1 followed by -1, -1 as we discussed. And this is the high frequency signal. So after every sample value, it changes from low to high and high to low. So this is the highest frequency signal. So now what we are going to do, we'll take the low pass filter, calculate the output for low frequency signal, also calculate the output for high frequency signal, and then we'll print the results, which will tell us that for a low pass filter, multiplication with low frequency signal gives you high result, whereas multiplication with the high frequency signal gives you low result. So that is what we are going to do. So YL, this is the output for the low frequency using the low pass filter. Okay, so BL dot star XL pointwise multiplication, and then you sum all the terms. So this will give you the output for low frequency signals for a low pass filter. So you display that. So this is just the display. In fact, similar calculation we are going to do for low pass filter for high frequency and print that. So YH, that is the output from the low pass filter for high frequencies. So BL multiplied by XH, YH again you find the sum and then print the output. And in fact, similar thing we are going to repeat for high pass filter, band pass filter, and band reject filter. Remember, for low pass and high pass we do only 2 calculations, for low frequency and high frequency. But for band pass and band reject we do 3 calculations for the low pass, high pass, and the medium frequencies. Okay, so rest is similar, except that some of these terms will be different because we'll be using different filters and similar signals. So this is the output from the high pass filter, and when the input is low frequency, so that is your dot star XL. Again you sum all the terms. So this is going to be repetitive now, except that your coefficients will change for different type of filter. So I won't take much more time now, but just simply show you the statements, be easy for you to understand. So this will be the output from the high pass filter when the signal is high pass. So that is the next calculation. Similarly, you do for band pass. So band pass filter, low frequencies output, and that you print. Then band pass filter, medium frequency signal, and sum will form the sum of the products, and you print the output. Then finally band pass filter, high frequencies, calculate the sum and print the output. And the same thing you do for the band reject filter. So band reject filter coefficients multiplied by low frequencies and print the output. Then band reject filter coefficients multiplied by medium frequencies and print the output. And finally, the band reject filter coefficients multiplied by the high frequency signal and print the output. So let us look at the results. First of all, we are simply printing the output coefficients. We are printing the output here, and what is shown is coefficients. So low pass coefficients, these are the coefficients, these are the high pass coefficients, band pass coefficients, band reject coefficients. And now let us look at the various outputs. So output from a low pass filter for low frequency input is 1, comparatively high, whereas the output from a low pass filter for high frequency input is minus 0.12. So you can see high frequency output for high frequency input is much smaller than this, and that is how the low pass filter works. If you look at the output from a high pass filter for low frequency input, it is low as you expect, but it passes the high frequency, so you get large output. Then for band pass, output from a band pass filter for low frequency input is low. For output for mid frequency input is large. Minus sign should not bother you. It simply means that your phase is 180 degrees, but the amplitude is large. And again, the output from a band pass filter for high frequency input is again low. So it passes the mid band of frequencies, so the band pass filter. Similarly, output from a band reject filter for low frequency input is high. For mid frequency it is low, that is the band that is being rejected. And the output for high frequency again is high. So that is how the band reject filter works. So in this session, we have tried to get some better insight into the working of the filter by doing some time domain calculations and writing a program for printing the result. And that's all in this particular session.